Newton's first law of motion. We're going to study the field of classical mechanics, basically mechanics that was done before the 20th century, and it allows us to describe a relationship between the motion of objects and the forces that act on them. Newton's first law is really the first part of classical mechanics, but we have to remember what we're talking about when we're talking about mechanics. We're talking about mechanics before quantum mechanics was invented and before relativistic mechanics was invented. So we're ideally looking at objects that are traveling far slower than the speed of light, gravitational fields that are much, much less than you find around a black hole, and objects that are a lot bigger than atoms, okay? And again, for our everyday experience, that's pretty much everything. Yes, if you want to go on to the atomic scale and study those interactions, we've got to switch to quantum mechanics. But for just about everything else, classical mechanics works pretty well. Even higher end parts of mechanics, something called quantum field theory, attempts to unite different forces with quantum mechanics. And there's even quantum gravity, which tries to unite relativistic mechanics with quantum mechanics. That's about all I know on that stuff. Quantum gravity is a little bit beyond my pay grade when we start talking about quantized pieces of gravity called gravitons. In any case, the history of classical mechanics starts long before Newton. Really, if we go back to the philosophers such as Aristotle, their naturalistic view of how the world worked attempted to create a nice model to predict how the heavens would operate, how things on the earth would operate. And much of their work was based on the heavens because it had very predictable motion. Aristotle popularized a geocentric model of the universe because he could not see parallax in the stars, and therefore he couldn't imagine that the earth was moving. This was a nice model in that it predicted what they saw, but it also felt right. It didn't feel like the earth was moving. It felt like, or appeared, that the sky was moving around us, that the sun and the moon would have their daily cycle, the moon would have its monthly cycle, and then the planets would have even longer periods of cycle than that. But basically, everything would seem to repeat itself over and over again. So this concept of having the earth in the center, crystalline spheres rotating around the earth on top of this, just felt very natural to the Greeks. Now, Aristotle not only didn't think that the earth was moving, he thought that it wouldn't be able to move. If it did, he supposed that everything on the earth would fall off. His idea was that there was a natural place in the universe for everything, and that everything would tend to, well, I don't want to use the term gravitate, would tend to move to that natural place. Objects that were made of more earth would tend to go to the earth. Objects made of water would tend to flow to the ocean. And then, of course, objects made of air would tend to go up into the atmosphere. So this would explain some of the behavior he would observe on Earth. A feather would fall slower than a coin because he would suppose that the coin was made out of more earth and the feather was made out of less earth. This led to his misconception that heavier objects fall faster than lighter objects because they're made of more earth. It's not true. A feather falls slower than the coin because air resistance is a greater force for its weight. In that air resistance opposes gravity much more for the feather than it does for the coin. Anything not moving to its natural place, Aristotle supposed would need a force. This was considered violent motion. You are violently moving an object from its natural place where it wanted to go. This had difficulty explaining such things as arrows and other projectiles in the air, but Aristotle attempted to explain this away by saying, yeah, well, the bow pushes on the arrow once it's in contact with the bow, but once it leaves, the air that it displaces comes around and pushes it from behind. That's pretty contrived, but to Aristotle, it was more about explaining the heavens because the Greeks really felt that the heavens were more pure mathematically, aesthetically, and while the heavens were incorruptible, what happens on the earth was corruptible. Now Ptolemy came after Aristotle. Ptolemy actually comes probably by the time the Romans had taken over Egypt from the Alexander's empire, the Macedonian empire. But Ptolemy tried to explain the problem of retrograde motion, where planets had a strange thing where they would move forward in the sky and then all of a sudden move backward and then progress forward again. Unlike the sun and the moon, the planets didn't have constant motion. They weren't pure cycles. They almost seemed like there was a cycle inside a cycle, and Ptolemy would explain this as the planets being on a circle on top of a circle. That would make sense. The problem with Ptolemy's model is it began to drift away from the natural aesthetic of the early geocentric model. The Earth was off-center. The motion would have this additional motion around some point on the circle. So it was a little bit difficult to accept, thinking that all motion had to be around the Earth and extended to this concept of epicycles. Well, a long time goes by, and it's not until the Renaissance that Nicholas Copernicus comes along. And Copernicus uses Ptolemy's model. He was interested in astrology. At the time, people believed that, yes, the heavens would influence events on the Earth, and Copernicus was one that studied this. Astrology was a much more noble pursuit at that point than it is today. So Copernicus attempts to look at Ptolemy's model and use the geometry of it to do calculations. He finds it very, very difficult. He tries to come up with not so much a cheat, but a way of simplifying the calculations by placing the sun at the center of all the motion instead of the Earth. And what this tends to do is not only make the calculations simpler, but the whole model looks a lot simpler. And Copernicus goes, aha, this must be the way that this works. He explained that the retrograde motion was the Earth passing an outer planet in its orbit, creating this forward and then backward motion because the Earth was moving faster than the planet, catch up with the planet and pass it. He published this in his book, The Revolutionibus. I didn't even come close to pronouncing that correctly, so please don't rewind. And in this, he was pretty much toward the end of his life. So he's publishing something that went against the church at the time, at a point in his life that the church probably won't be able to get back to him and excommunicate him for publishing heretical ideas. Now, the reason why the church saw this as such a heretical idea is many of the theologians, surmised that according to the Bible, the way that they interpreted the Bible at least, that the Earth had to be the center of the universe. Well, obviously, placing the sun at the center of the universe, it caused a problem for these theologians. So Copernicus publishes his book. Initially, it's published just as a theory. Right before he dies, he republishes it saying, no, the sun's actually the center of the universe. He dies, the church is unable to do anything about it. So this Copernican model of the universe becomes a very controversial one. It's banned by the church, and essentially everybody's told to just, leave it alone, stay away from it. Stick with the geocentric model. A little bit later in time, another astronomer who's largely forgotten about, Tycho Brahe, begins to do his own observations, but like Copernicus, some of the work that Brahe does will actually have people question what the Greeks had taught us. Now, he's born to Danish nobility, so he's very rich. His father had connections with the king of Denmark, and the legend goes that he lost a duel with another student, he lost his nose in a duel with another student, and as a result had to wear a prosthetic nose made of gold and silver. He was also extremely arrogant, and was not the stereotypical nerd you would have thought of back then. He would throw tremendous parties and would attend parties himself. It's even known that he owned a moose, and he lent his moose out to a friend during one of their parties, and the moose was killed when it wandered out a window and fell from a great height. So very unique, arrogant, very unusual. But Tycho changes the way of doing astronomy because, well, like Hipparchus in the ancient Greek time, he makes measurements, but he makes extremely precise measurements. His observatory was a castle-like structure. It didn't contain a telescope. It contained quadrants, and it was known as Uranoborg. And he could actually sit in some of these protractor-like devices and measure the position of planets, measure the position of the moon, measure the position of stars. And these very accurate measurements became important later on. Now, Tycho's model of the universe was sort of a compromise. He didn't want to get in trouble with the church, so he still placed the Earth at the center. But it was almost like a modified version of Copernicus's model. Here you would have the Earth at the center, and the Sun orbiting the Earth, but all the planets going around the Sun. Now, Tycho made two important observations that made what the Greeks had said, the Greek philosophers said, suspect. One, he observed a supernova, and by doing parallax measurements, he saw that this new star was very far away. Nova, to this point, these new stars, were thought to be atmospheric phenomena. Tycho clearly showed that this was very, very far away, and it showed that the heavens were not uncorruptible. They did change. He also observed a comet. He was fortunate enough to live at a time where both a comet and a supernova appeared, showed that the comet was actually orbiting out by the other planets, whereas before this, many people thought that a comet had to be an atmospheric phenomenon again, that it couldn't be celestial because the heavens were supposed to be perfect. So Tycho pretty much proves that the heavens do change. And this is important because this is going to allow Galileo to chip away at some of what was taught before that. It's not quite clear what happened, but in Denmark, King Frederick passes away, and Tycho falls out of favor with King Christian, the son. Not quite sure what happened. Some say that Tycho had an affair with the former queen. Some say that Tycho didn't keep up the chapel on the island like he was supposed to, that he put all his money into the observatory, and the king had designated funds for this. In any case, Tycho and King Christian don't get along. So Tycho packs up and leaves Denmark to go to the Holy Roman Empire, which is sort of a conglomerate of a lot of Germanic states, which would be present-day Germany, Czechoslovakia, and even part of Austria. King Rudolf is the emperor of all these states, and he's really happy to have Tycho in his charge. Basically, if you're a ruler back then, you would want to have the greatest thinkers. A show of power was to have the greatest musicians, all these different things. Mozart and Beethoven were funded by very rich rulers. So King Rudolf wanted the prestige of having the greatest astronomer of Europe in his empire, but he was a little bit suspect about Tycho because he already had a fallout with another king. So he has Tycho, take on Johannes Kepler, who is a very prominent astronomer in his own right. But Kepler is basically there as his insurance policy. If Tycho goes off and leaves, Kepler would have all his work and be able to continue Tycho's work, which was being funded by the Holy Roman Empire. Well, Tycho didn't trust Kepler because Kepler was a very capable astronomer, and he was afraid that Kepler would become more famous than Tycho. Well, that happens anyway. So he gives Kepler his most difficult data. Tycho's measurements of Mars just don't seem to make sense to him. So he says, I'll give Kepler this garbage data and let him just ponder it for a while. Unfortunately, Tycho dies in 1601, and while Tycho becomes very famous for popularizing observational astronomy, Kepler eventually becomes more famous because he realizes that Tycho was having so much problems with the data on Mars because planets go around the sun in ellipses rather than circles like everybody thought. So finally we get to Galileo. Galileo is born in 1564. He's a contemporary of Kepler. They actually corresponded. And while Galileo doesn't invent the telescope, he improves existing telescopes so much that basically they can be used to observe the heavens. They're still nowhere near the quality we have today, but they're a big improvement in where they were. So Galileo spends most of his life basically trying to provide evidence for Copernicus's theory and trying to disprove what some of the Greeks had taught before. Galileo comes up with the theory of inertia, the idea that objects in motion tend to stay in motion, objects at rest tend to stay at rest. It's actually Newton's first law. Newton gives him credit, but we call it Newton's first law. And this strongly disagrees with Aristotle's idea of natural and violent motion. So again, you see where he's going. He's trying to show, well, the Greeks were wrong about a lot of things. Can't they be wrong about the geocentric model? Can't we have a heliocentric model? So again, he shows that objects speed up when rolling downhill, they slow down when going uphill, and they'll always try to reach their original height. Thus, if they're on a level surface where there's no friction at all, the ball should roll on forever. And it's not really going anywhere, right? It's just continuing on. Different from Aristotle's view. Aristotle said, no, things will go to their natural place in the universe. The ball will try to go to the earth. Well, it's basically sitting on the earth, but it's still rolling. No forces. What's going on? Galileo stated, an object will move not because of forces and not before its tendency to go to its natural place in the universe. An object will continue because that's its property. If it's at rest, it'll just stay there. If it's moving, it will tend to keep going because of its inertia. Galileo studied gravity. Now, he did not drop objects from the Leaning Tower of Pisa. This is a myth. He taught in the town of Pisa, but he didn't do this. He showed that going down inclined planes, objects of different mass would accelerate at the same rate. He also used the telescope. Again, disprove what the Greeks had taught. The Greeks had taught basically that all the heavenly bodies were perfect. Okay? The sun was a perfect sphere. The moon was a perfect sphere. All motion in the heavens was around the earth. Galileo, first of all, looks at the sun. There's a little bit of a problem because this probably caused him to get cataracts. And even though he used smoked glass to reduce the intensity of the sunlight so he wouldn't be blinded instantly, the exposure to ultraviolet light did eventually destroy the lenses in his eyes, giving him cataracts. But he clearly showed that sunspots existed on the surface of the sun. The sun was not perfect. On the moon, he would observe mountains and craters. The moon wasn't perfect. Probably the most important piece of evidence was the phases of Venus. He watched how the Venus became a thin crescent as it got closer to the Earth, and as it moved away from the Earth, it became a waxing gibbous. This is important because it showed that instead of going around the Earth in a circle, like the planets were supposed to, Venus was getting closer and further from us based on where it was in the sky with respect to the sun. It was going around the sun very clearly from Galileo's data. He observed star-like objects going around Jupiter. Again, motion was not around Earth in this case, it was around another object. As we said, not only was the moon not perfect with craters and mountains, those craters and mountains would appear to obey the same laws of optics as objects casting shadows on the Earth. So this is very, very important. And originally, Galileo was a little bit shy about this. He just posts his observations in a book called The Sidereal Messenger. And this is published in 1610. There's a little bit of questions about what Galileo is doing, but for the most part, because he just publishes his observations, it doesn't really cause a lot of problems. The problems come when he publishes his next book. Gets a little more bold. He's becoming more famous now. Dialogue concerning two chief systems of the world, Ptolemaic and Copernican. In this book, he does it, as the name implies, as a dialogue between two people. Salviati, who would support the heliocentric model, and Simplicio, sounds like simpleton, who supported the geocentric model. While the book was not intended as a slight to anybody, the book was seen by some of Galileo's opponents as being an attack on the Pope, where they argued that Simplicio was the Pope, and Salviati was Galileo. Now, the Pope was actually friendly with Galileo. They knew each other before the Pope was elevated to pontiff. However, the Pope was really not wanting to get involved in any controversy and did not do any favors for Galileo. As a result, Galileo was brought before the judicial branch of the Vatican, if you will, known as the Inquisition. And the Inquisition, of course, found Galileo to be guilty, and they even forged some documents to show that he was told not to teach this, and he taught it anyway. Galileo was acquitted in 1992, but obviously he was long dead by then. And Galileo was placed under house arrest. By this time he's pretty much blind, so a wealthy benefactor takes him in. They agree to house arrest. But Galileo continues his writing, and he writes discourses and mathematical demonstrations concerning two new sciences, and this was probably his biggest work, and it becomes the most important book of its time in physics and mechanics until Newton's Principia. The book is rushed off out of Italy in secrecy, and when Galileo dies, he's actually buried in secret so that he could get a Christian burial. The belief at that time was if you don't get a Christian burial, you went to hell. It wasn't until 1737 that his body was actually moved to his family crypt and he was buried there. So looking at this, Aristotle, the Greeks, their contribution was, well, coming up with a naturalistic model for how the universe worked. Ptolemy used epicycles to correct Aristotle's model of the universe and made a more accurate prediction as a result. Copernicus develops his heliocentric model. Tycho's observations show that the ancient Greeks were wrong about many aspects about the heavens, especially the fact that they never changed. And Galileo develops the concept of inertia and proves Aristotle's theories of natural and violent motion to be false. Okay? This inertia, this law of inertia, is really the basis for Newton's first law.